Hello and welcome to this video where today we're going to be starting off by looking at the basics of waves, and we're going to look at progressive waves. In other words, waves that move from one place to another. Now at GCSE you met the concept of a wave, and this is basically what a wave does. So a wave is something that transfers energy from one place to another. And this is your kind of like traditional picture of a wave. It's a transverse wave. In the next video we'll have a look at the difference between a transverse and a longitudinal wave. But as you can see, basically it's got some peaks and it's got some troughs. So they're two kind of like concepts that we have to know a little bit about because they're often talked about. So that's a peak up here, and the kind of bottom bit down here, that's called a trough. That's a trough. And what we've done is we've got this thing here. Now this is the displacement. So we've got these particles, and these particles normally would be sat on this line. So if the wave wasn't happening, they'd be sat on this line. This line's also got a special name. So because this is where they would normally sit when the wave wasn't there, then they'd normally just sit there. So the resultant force acting on these particles would be 0. So in other words, they'd be in equilibrium, because equilibrium basically means that the resultant force is 0. So this line is called the equilibrium line. This is where the particles normally sit. But because the wave is happening, it's because energy is being transferred, these particles are being displaced away from the equilibrium line. And as we'll see in a second, and as you know, these things just oscillate upwards and downwards. So each of these particles is displaced away from this line. If we look at actually what it looks like as it's moving, this is kind of a very rough animation of what a wave looks like. So if you think about it, and we put all of those things that we've already had a look at together, a wave transfers energy from one place to another. In this case, the energy is being transferred from the right-hand side to the left-hand side. And if you look at this peak here, it's moving in that direction. So you can tell the direction that this progressive wave is moving. It's called a progressive wave because the wave actually moves from one point to another. As you'll see in about a week's time or so, or you'll see at the end of September, there's also a thing called a standing wave, which is different from these things. So what we've got is, if we look at one particular particle, let's pick this one here, you can see that all this thing does is this thing oscillates. In other words, it just goes backwards and forwards, or in this case up and down. But what it doesn't do, really importantly, is it doesn't move from one end of this wave to the other. So the particles don't actually move from one end to the other. The only thing that's moving is energy, and that's really important. So as you can see, if we take a snapshot of our wave like this, we go back like that, then we've labelled these things. So we've got this thing here, so this is the maximum displacement, this part here. All of these particles have also got a displacement, so that displacement there is basically 0. There's a small displacement there, a bit bigger displacement there. The biggest displacement happens at the peaks and also at the troughs. And so that brings us on to our definitions of these different parts of the wave. So we've got this amplitude here. The amplitude is the maximum displacement from the equilibrium position. So if you remember, equilibrium position or the equilibrium line is this line here. The maximum displacement means the most displacement away from that line. So the most displacement happens at a peak. So the amplitude is basically there. Amplitude is given the symbol A, so rather than write amplitude as a full word, we just give it a symbol A, and because it's a distance from there to there, we measure it in meters. There's also something else that you met at GCSE, which is the wavelength of a wave. Often at GCSE, it's simply the distance. You say it's the distance from one peak to another peak, or one trough to another trough. Now we're looking at A level. We kind of need a better way to describe this. So the wavelength it's still represented by the same distance, but it's described like this. So the wavelength is the shortest distance between 2 points that are in phase. We'll have a look at a phase towards the end of this video, but essentially what it means is that if we have two particles that are doing exactly the same thing, so if we can possibly have a look here, you can see that like this particle and this particle, if you have a look at them, it's very difficult to see, but if we can try and kind of grab the two particles, this one and this one, if you were able to kind of watch both of those at the same time, you would see that they both went up and down and did exactly the same thing. Because they're doing exactly the same thing, you would say that they're in phase. We'll have a look at that in a bit more detail in a bit. And the shortest distance between two particles that are in phase is called the wavelength. Wavelength, again, because it's a distance from one place to another place, is measured again in meters, and it's given this symbol here. So this is the Greek letter lambda, and that's the symbol for wavelength. So instead of writing wavelength, we can just write lambda down. Now, so this is essentially, if you like, a photograph of a particular of a snapshot, if you like, of the animation we had before. That's the displacement, and this is the distance from a certain point, and over time this wave would change. We can also kind of plot a different graph, because that's essentially what this is. This time, but we can plot a graph of the displacement again, so how far a particle is away from the equilibrium line, against time. Now, the important thing to realise about this thing is we're only thinking about the displacement of one particle and how its displacement changes over time. So basically, if we go back again to our animation here, let's say we picked this wave, this point here, and we followed it. What we would do is basically start our stopwatch when it got to the equilibrium line. So if we wait just 1 second, so if we started our stopwatch now, and then basically measured the displacement at certain times after that, and then what we would do is we would plot this graph here. And what this shows us is that when the time was 0, basically the point was on the equilibrium line. A little bit later on, it was up here. A bit later on, it was up here. So this shows us how the displacement of that one particular particle changes as the time changes. And the wave basically looks exactly this. It looks the same, but the distances now mean different things. The amplitude is still the same, because this is still displacement just the same as it was here. So this amplitude and this amplitude are still the same. So we've still got our amplitude measured in meters. The difference is this: if we measure from a peak to a peak, or from a trough to a trough, or we go from here and we go up, down, back to essentially the equivalent particle on this side, then this distance no longer represents the wavelength, because wavelength is measured in meters. This x-axis is measured in seconds, so we can't have a wavelength that's measured in seconds. So this means something else. If you think about it, what this means is if you started your stopwatch here, the amount of time it's taken, the particle's gone down to the bottom, and that's at this time here, and then it's gone back up to the top, and that's at this time here. So the amount of time it took for that to happen is the amount of time from here to here. So that's the amount of time it took this particle to perform one cycle or one oscillation, and that's given a special name. That's called a time period. It's given the symbol t, so instead of having to write out the time period as a whole, it's given the symbol t, and because it's a time, it's measured in seconds, and it's simply defined by this: the time taken for one complete oscillation. In other words, the time it takes to go from here down to the bottom and back up again. Now, time period is really useful if you want to know, for example, how long one oscillation lasts for, but often we don't want that. Often we want to know kind of like how many of these oscillations happen in 1 second, and for that instead we use the frequency. Frequency is given the symbol f, which is fairly easy to remember because it's the same letter as it starts with, but it's measured in this unit, so it's measured in hertz, and Hz is the shorthand for hertz. Now it's really, really important that that's a capital H and that's a little z. If you write it any other way, then basically you'll get the unit wrong if you're asked for the unit of frequency. It's defined like this: it's the number of complete waves that pass a point in 1 second or each second. So that's your definition of frequency. Now if you think about it, these two are linked together, because this is the time for one complete wave, and this is how many waves essentially fit into 1 second. So the relationship between these two, so the time period is equal to 1 over the frequency. And if you want it the opposite way around, you can rearrange that. Frequency is equal to 1 over the time period. And these two things are really, really useful. And basically, so once you know the frequency, you can work out the time period and vice versa. Now, when it comes to definitions, you need to learn all 4 of these definitions. If you're watching this video as part of your Year 12 induction homework, you must learn these definitions because you're going to be tested on these when you first start back in September. So, we've now got some definitions, and we know what the frequency is, what the wavelength is, etc. We're going to look at the wave speed equation, and I'm going to derive it just so you can see roughly where it comes from. Now from GCSE, if you think about what you did at mechanics, you learnt that speed is basically the distance divided by the time. Now if you think about this in terms of waves, we're going to think about what happens in one oscillation. Now in one oscillation, the distance that the wave travels is from, if it's going from here to here, it travels from here to here is just one wavelength. So the distance is one wavelength. And the time it takes for that to happen is the same as the time it takes for this particle to go down and back upwards again. In other words, it's the time period. So it's given by this thing. So I'm going to write that in a funny way because that's the same as the wavelength multiplied by 1 over t. That's exactly the same thing as that. But we know from before that 1 over the time period is equal to the frequency. So you end up with this thing. And so you end up with, altogether, this. And all I've done is, instead of writing v for velocity, I've written c. That's just basically that's just it's a different symbol for the same thing. So c is the wave speed. That's the wave speed, and that's measured in meters per second. And I'm going to write like that. So that's meters seconds to the power of -1. F is our frequency, which is measured in hertz, and lambda is our wavelength, which is measured in meters. So if we know two of these things, we can work out the third one. So let's have a look at that. So here we've got a quick worked example. I've got a wave. It's traveling at a speed of 40 meters per second, and it has a wavelength of 20 meters. I want to calculate the time period of a wave. So this is what I'm going to do. If I want to calculate time period, there's only one equation I can use at the moment, and that's this one here. I can't do anything else because that's the only equation I've come up with. So if I want to know the time period, I need to work out the frequency. I've got an equation with frequency in it, and that's this one. So what I could do is I could be clever. I could either substitute that into there and get, but I'm not going to do that. All I'm going to do is work this out. I'm going to work out the frequency from here, and then I'm going to substitute into this second equation to do that. So what I want you to get into the habit of doing is, number one, writing down all of the equations that you need. So we've done that. Number two, I then need to write down what I've got. So if I look at my question, the speed is 40 meters per second. So that's that one. And I know the wavelength of the wave is 20 meters, so I could write that down. Wavelength is equal to 20 meters. So that's the information I've got. These are the equations I've got. So the very first thing I'm going to do is work out the frequency, because that's all I can really do. So frequency is equal to the wave speed over the wavelength. So if I look at my numbers now, c is 40. The wavelength is 20. 40 over 20 is just 2. So that gives me the frequency of 2 hertz, capital H, little z. So I'm halfway there. I've worked out what the frequency is, but I haven't answered the question because I want the time period. So now I use my other equation. Time period is equal to 1 over the frequency, which is equal to 1 over, now the frequency I've just worked out to be 2. So therefore that time period is equal to 0.5 seconds. So I've answered my question. So that's how you would use that to actually calculate the speed of that, or the time period of that particular wave. So I said we'd have a look again at phase and basically what phase difference meant. So what we've got here now is we've got essentially a stretched out wave. We've got a wave with a number of peaks and troughs. And we're going to basically look at the relationship between these particles here. And here's my animation again of this transverse wave. And what I've tried to do is I've tried to draw two lines that are exactly one wavelength apart, because it's going to help us. Because what we need to do is, if we look at this particle here and we look at this particle here, they're doing exactly the same thing. So if they're doing exactly the same thing, that's the same as, so if we look at this, that's the same as, that's the peak and that's the peak at the same time. That would be this one and this one, but also this one. And if the wave carries on, the next one, and so on. So what we would say is that C, G, and K, you could say that we would actually say that they are completely in phase. And they're in phase with each other basically because they're doing exactly the same thing. Now, what you can also do is you can also look at to see the relationships between things that aren't in phase. If you think about it, if you think about this one here and this one here, for example, that's the same as thinking about a peak and a trough. So if we think about, if we can get this, so I've got a peak and a trough. And if I think about what's happening with that, when this one's at the peak, it's going to start going downwards. When this is at a trough, it goes upwards. So they do exactly the opposite thing. So in that case, C and E, so C and E are completely out of phase with each other. So if you see the words in phase or out of phase, or completely in phase and completely out of phase is the better way of saying it, then basically it means that they're oscillating exactly the same. These are oscillating in exactly the opposite way round. Now that doesn't help if we want to compare like C and D, for example, because that's going to go downwards. This one's potentially going to go upwards, depending upon which way the wave's going. But they're doing opposite things, and we could do with a better way of actually saying, well, they're in phase or they're out of phase or whatever. And we can do that because if I look at these things, there's an equation I can use. Now, we're only going to look at this particular row here. There's also, because once you know how to convert from degrees to radians, that's fairly straightforward. But there's an equation where you can calculate the phase difference between particles on a wave, or if you've got two waves, you can calculate the phase difference between two waves. But we're just going to concentrate by looking at the particles on one particular wave. So we said basically if we've got A, E should basically be completely in phase. Now, what we're going to do is we're going to think about essentially what happens in a circle, because waves and circles are linked a lot, really. And in a circle, we have 360 degrees, like that. So in other words, if we start here and we go 360 degrees around, we get back to where we started from. So any multiple of 360 degrees, 360, 720 means we've gone round twice, but we've got back to the same point. 360 degrees basically means that we're back to where we started from. So if we're here and we move a phase difference of 360 degrees, what it means is we're at the next point that is doing exactly the same thing as that. In other words, it's completely in phase. So that would be E. I would be like going around our circle twice, because we've gone 1, 2. So that would be 720 degrees. And the M would be like 3 times, 1, 2, 3. So we've kind of gone around our circle 3 times. No matter what we've done, we've gone back to the same place. So these things are all in phase. They're all basically at the same point on our circle. So if we're representing one whole wave by 360 degrees, what we can then do is we can split up the rest of the wave into degrees. So if we think about from here to here is 360 degrees, so from here to here is 180 because it's just half of it. So if two particles are completely out of phase with each other, so they're doing exactly the opposite thing, then they must be half a wavelength apart. And if they're half a wavelength apart, what it means is that they're 180 degrees apart. So that means, so looking at this, A and C should be 180 degrees apart, and that's what it says in our table, and that's right. It also helps with A and B, because we couldn't really explain what was going on with B before, but because we now know that in one full wave is represented by 360 degrees, from here to here, that's 90, because it's a quarter of a wavelength along. So therefore we've got 90 degrees, and we can do that with any point that's on this diagram. In actual fact, you can do it with any point at all, because you could do it with, for example, this point and this point here. Now, what we'd have to do is, what we've really been doing is we've been working out the fraction of a wave. And so what we've been, if we think about, let's go back to this, let's go back to C, for example, because that's an easy one to think about. What we said was that the whole wave is 360 degrees, but the distance from there to there is half a wavelength. So it's half of 360 degrees. So if we can work out the fraction of a wavelength that we go from our starting point to our next point, and then multiply it by 360 degrees, that'll tell us what the phase difference is. That's where this equation comes from. This x here is essentially the distance in meters, from one particle that we're interested in to the next particle. And lambda in exactly the same way as we saw before. This thing here is the wavelength, and again that's in meters. And what this really gives us is the ratio between the distance and the wavelength. So it gives us the fraction, if you like, of how far we've had to move along this wave. And then if we multiply that through by 360 degrees, it tells us essentially how many degrees out of phase with each other these things are. And if you use this equation for any of these things here, you'll get exactly the right numbers that's in this particular table. When it comes to looking at these things, when it comes to looking at radians, we'll have a look at this. Basically, radians are just another way of measuring an angle. Instead of having 360 degrees in a circle, we say that there are 2 pi radians in a circle. So if you go 2 pi radians around like that, then you've done a full circle. So 360 degrees is 2 pi, 180 degrees is just 1 pi, 90 degrees is pi by 2. So, and actually converting between radians and degrees is really easy. Because if you know that if you know that 180 degrees is 1 pi radians, you can work out, for example, what 70 degrees would be, simply by looking at what 1 degree is and then multiplying it by 70. We're not going to look at that in this video. We'll look at that a bit later on. So we're going to do one more worked example. What I've got a wave. It's got a wavelength of 2 meters, and there are 2 particles on this wave, and they've got a phase difference of 200 degrees. I want to know how far apart these particles are. So I've got a wave like this. I've got something here, for example, and something, for example, here. And now I know that the phase difference between these two things is 200 degrees, and I know that the wavelength is equal to 2.0 meters. So I've got 2 significant figures there and potentially only 1 here. I want to know how far apart they are. So what I would do is, these are the numbers that I know already. So I've kind of written those down. That's my phase difference, that's my wavelength. So I've written down what I know. I'm now going to write down the equations that I know. So the only equation I really know that's got anything to do with this is this one, which we met a second ago. Okay, and that's the phase difference. I know that, so that's fine. This is the distance. Well, I want to know how far apart these particles are, so that's that one. And I also want to need the wavelength. I've got that over here. So I can rearrange this equation. So if I'm going to rearrange this, so I get, if I multiply by lambda, I get the phase difference times lambda is equal to 360 times the distance. And now if I divide both sides by 360 and just swap sides around, I get x is equal to phase difference times the wavelength over 360, like that. So now I've got an equation that I can use because I know these two numbers. So the phase difference was 200 degrees. The wavelength was 2.0 meters, and I divide by 360. And then I just get my calculator out and I get 1.1111. So I've got kind of like 2 significant figures there, 2 significant figures there. I'm not sure how many significant figures this is, but it's potentially 1. So what I'm going to do is I'm going to write this down to 2 significant figures. So if I do that, I get 1.1 meters. So what I'm really saying is that the whole wave has a wavelength of 2 meters, but if any particle that's 1.1 meter apart is essentially going to be out of phase by 200 degrees. So that was the first video looking at waves on progressive waves. We had a really quick look to see basically what waves look like. This is a definition that you need to know. We then also had a look to see, we had 4 more definitions. So we've got these 4 definitions again that you need to learn off by heart. And then we had a look at phase difference and look to see how you would actually calculate the phase difference of 2 particles on a wave. So that's it for progressive waves. Thank you very much for watching, and I'll see you again soon.